Now, hello, good people. Today we are talking about momentum and impulse. We're going to start by talking about momentum today, and I'm going to start you off with a quick definition. You've heard of momentum before in your everyday life because we talk about momentum. If something has a lot of momentum, well, that means that it's really, really going and it's going to be hard to stop. Here are the definitions that I use for momentum. I say that momentum is inertia in motion or how hard it is to stop a moving object. Momentum is inertia in motion or a measure of how hard it is to stop a moving object. Now, you could probably pretty intuitively figure out what kinds of things affect momentum. First, I ask students if there are baby geese crossing the road and a Toyota Camry is careening down the road at a ferocious speed of 30 miles an hour, then that would be a hard situation. And I say, but another situation could be if little baby geese are crossing the road and a Toyota Camry is careening down the road with a ferocious speed of 5 miles an hour. And I ask students, which one feels like a trickier situation for you? Which one do you feel the most comfortable intervening in? And they say, well, Miss Wilson, the situation where the Toyota Camry is going 30 miles an hour, that's a trickier situation. And I feel way more comfortable intervening and trying to stop the moving car if the moving car is going 5 miles an hour. And I say, yes. So how hard it is to stop a moving object absolutely depends on how fast it is going. It depends on V, the speed. But that's not the only thing that it depends on. You see, if you had a car, let's say that there was a Toyota Camry careening down the road heading towards the baby geese, and it's going a speed of 20 miles an hour. Or there is a semi-truck careening down the road at 20 miles an hour headed towards the baby geese. Which one would you rather stop? And the people of my classes always say, I would rather try and stop the Toyota Camry than the semi-truck, Miss Wilson, because it has way less mass. And so it has way less inertia. And so it is easier to accelerate and hence easier to stop. And I say, yes, absolutely. That is the other thing that affects momentum. Two things that affect momentum. First, how fast it's going. And second, how much inertia it has. Those two things in combination with each other will impact how hard it is to stop a moving object. Hence, that gives us the formula for momentum. Momentum is mass, the inertia of something, times V, how fast it's going. And if you had to choose one letter to represent momentum, you would, of course, choose the letter P. Lowercase letter p is what we use to represent momentum, which is why in my classes I always write it as momentum with a silent letter P at the beginning. So this equation is absolutely worthy of your bag of tricks. As you're adding it to your bag of tricks, let us talk a little bit about the units here. You already know, of course, that the units of mass are kilograms. And you, of course, do know that the units of velocity are meters per second. And so the units of momentum are kilograms times meters per second. Now, this is the part where I normally would say, and all the good physicists of the world got very, very tired of saying kilograms meters per second, kilograms meters per second, kilograms meters per second, kilograms meters per second over and over again, because that's a very hefty thing to say. But actually, they didn't get tired of saying that over and over. So we are left with units for momentum of kilograms meters per second. And those are our units of momentum. So momentum has units of kilograms meters per second. Let's try a quick little practice problem here. Open up your textbook to page 199. We're going to take a look at question number 1 together. Page 199, question number 1 says that a deer with a mass of 146 kilograms is running towards you head on with a speed of 17 meters per second. Now, I do have to ask you exactly what you did to get yourself in this situation, because this is insanity. And 17 meters per second, well, that is quite fast. It says you are headed north. What is the momentum of the deer? Okay, well, we start by writing our knowns and unknowns. First, the mass of this deer is 146 kilograms, as given to us by the problem. The velocity of the deer is 17 meters per second. Let's talk about direction. If you are headed north and the deer is headed straight on towards you, then the deer is headed south. So we say that the direction of the deer is south. If you would like to do something like this and say, I'm going to call south the positive direction, you are more than welcome to do that. Then, lastly, we are looking for the momentum of this deer. We would start with an original equation. We would say that the momentum of the deer is equal to the mass of the deer times the velocity of the deer. We would plug in for the mass of the deer 146 kilograms. We'd plug in for the velocity of the deer 17 meters per second to the south. You do most certainly need to include direction because we got velocity here, and you'll notice that momentum does have direction. When you type that into your calculator, you should get 2,500 kilograms meters per second. Wow. To the south. And there is your final answer. Not too bad. Okay, now let's talk a little bit about momentum conceptually. If I had two carts, here is a cart, and here is another cart. Wait, there's one. Here's another one. Don't they look so similar to the carts that you use in your labs? Okay, here are two carts. Let's say that on top of this one here, I set a stack of masses. So I add a ton of extra mass onto this first cart. We shall call this first cart cart 1. And suppose then that I have this second cart 2, which doesn't have any mass. If both are not moving, which has more momentum, cart 1 or cart 2? You would say, Miss Wilson, come on. They both have the same momentum because their momentum is 0 if they're not moving. And that is absolutely true. Now here's a question. If I push them both so that they have the same velocity, who has more momentum, cart 1 or cart 2? You say, Miss Wilson, cart 1 would have more momentum because it has the same velocity, but it has more mass. So greater mass means greater inertia, which means it would be harder to stop. So cart 1 has more momentum. And that's absolutely true. Now, what if I said, is there a way that you could push cart 1 and cart 2 such that even though they have different amounts of mass, they could have the same momentum? You would say, well, sure, Miss Wilson. What I would do is I would push cart 2 much more than cart 1. So I would give cart 2, it has less mass but more velocity. Cart 1 has less velocity but more mass, and so they'd end up both having the same amount of momentum. And I'd say, yes, absolutely, that's totally true. These are a few little conceptual examples here to help get you set up for some lab work that we'll be doing in the future. Let's go ahead and take a look at impulse next. Impulse in physics is not defined as purchasing something that you did not plan on purchasing. That is not what impulse is. Impulse in physics is a change in momentum. Impulse is defined as a change in momentum. Anytime something changes its momentum, we have an experience of impulse. So, for example, here's Connor. Connor the cactus. If Connor the cactus is moving and then Connor stops moving, well then Connor has experienced a change in momentum because Connor was moving and then is not moving, and so that would be Connor experiencing an impulse. If Connor was moving and then Connor starts slowing down, we would call that a change in momentum. If Connor is moving and then Connor starts speeding up, we'd call that a change in momentum. If Connor is not moving and then Connor starts moving, that's a change in momentum. Anytime Connor is changing his velocity, he is changing his momentum. And so a change in momentum, you could see, we can most of the time break it down and say that an impulse or a change in momentum is normally going to be a mass times a change in velocity. Because most of the time when you're experiencing an impulse, it's your velocity that's changing, not your mass. Now a short derivation over here for you. Let's get out the little pen. Here's a short derivation for you. If I have mass times velocity, do you agree it is totally and completely fair game to multiply top and bottom by delta t like this? So that I have mass times velocity times delta t over delta t. Isn't that still just multiplying it by 1? And all the mathematicians would say, yes, that is a very totally fair move. You have still written the same expression. Now check this out. If I multiply by delta t over delta t, then I get mass or velocity over a delta t, a change in velocity over a change in time, which you know is an acceleration. And finally, you know that a mass times an acceleration from Newton's second law is a force. And this should make some sense to you. This gives us a third equation for impulse, so that we have not one equation, but three equations. We say that impulse is a change in a change in momentum, which means it's a mass times a change in velocity, or a force that's applied over a time. Hey, doesn't it make sense to you based on what you already know about the world, that if you want to change your velocity, that's going to probably require a force? Isn't that Newton's second law and also Newton's first law, the law of inertia, that if an object does not experience a force, it will not change, and if it does experience a force, that's how it will change its velocity. So a force is required to make a change in velocity, and in order to have a change in velocity, that force has to be applied for a certain amount of time, a delta t time. All of these represent impulse, and so we have not one equation for impulse, but actually three equations for impulse. And if you had to choose one letter to represent the word impulse, then you would, of course, choose capital letter J. Which is why in my class I do not call it impulse, but instead I call it Gympulse, or Gym for short. Please don't tell any physicist of the world that I call it Gympulse, because that's absolutely and totally ridiculous. We call it Gympulse because it's represented with a capital letter J, and that gives us not one but three equations that are all worthy of being added to your bag of tricks. Now, let's talk conceptually through the meaning of these equations. In class, I do a little demonstration on this day where I say, hey, suppose that I had a beaker. That is a very light gray. Let's choose a slightly less light gray. So sorry. Okay. Suppose that I have a beaker. And what I do is I hold a little egg above this beaker like this, and then I drop the egg down into the beaker. And when I drop the egg into the beaker, then, well, you could probably guess, if I drop the egg into the glass beaker, then I end up with shards of egg at the bottom of a glass beaker. And there's like this yellowy stuff that's leaking out all over the place, and we call that the egg yolk. And, yeah, that's pretty much like the situation. It's just a little bit of a mess in there. Now, that's what happens if I drop the egg down here at the bottom of the glass beaker. But then I do something else. In my next experiment in class, I take this egg and I drop it into a glass beaker once again, but this time I take a little bit, here's my glass beaker, here's my egg. Wow, that's a large egg. Let me try again. Let's have a same-sized egg so that they can have the same mass. Okay. Pretend these are the same size. Next, I drop this egg into the beaker, but this time I throw a bunch of toilet paper into the beaker before I drop the egg. And when I drop the egg lands inside of the beaker, and when it lands inside of the beaker, I drop it from the exact same height, and it lands very safely inside of the beaker, and it rests upon the toilet paper as though it is a little bed. And I say to the students, okay, question for you. Which egg experienced a bigger Gympulse? The first egg, which we shall call egg number 1, which hits the bottom of the glass beaker, or the second egg, which we shall call egg number 2, which hits the toilet paper? And the answer is the same. Here's why. Both eggs, the first egg and the second egg, they both experience the same change in momentum. They both had the same mass-ish, relatively speaking. They both had relatively the same mass, and they were both going the same speed until they were both not moving at all. And so they both experienced a point where they were going fast, and then they weren't going anymore. And so both had the same change in velocity, and both had the same mass. And so if both have the same mass and both have the same change in velocity, then they both have the same change in momentum. And so they both actually experience the same Gympulse. But they both don't experience force and time the same way. Check it out. The first egg experiences the same gympulse as the second egg. They both experience the exact same size change in momentum. However, for the first egg, when the first egg hits the bottom of the beaker, the glass takes no time in slowing it down. The glass does not say, "Oh, hello, little egg. Let us gradually slow you down from going very, very fast to now not moving at all. Let us give you plenty of time to adjust." No, that is not what the glass does. It hits the bottom and it stops almost immediately. I mean, it takes some time. It takes some time for that glass to put a force on that egg to slow it down, but it takes very, very little time. And so the egg stops. That change in momentum happens very, very fast in a very short amount of time. Which means that in order to stop something very, very fast, in order to take something that is moving and to make it go not moving as quick as quick as possible, that's going to take a really, really big force because you had a big acceleration. So the glass provides a big force on the egg in a very short amount of time that makes the egg stop moving. Well, meanwhile, when the egg hits the toilet paper, the egg that hits the toilet paper very gradually slows down as it gradually compresses the toilet paper. So it pushes down on the toilet paper and the toilet paper says, "Ah, yes, will you gradually come to rest?" And it does gradually come to rest over time, which means your delta T for your egg that's hitting the toilet paper is very big. It comes to rest over time, which means that the toilet paper doesn't make it slow down very quickly. And so the toilet paper only has to apply a very little force. So the toilet paper applies a little force over a long time to make it go from moving to not moving. The glass provides a big force in a very small amount of time to make it go from moving to not moving. And so the egg breaks in situation 1 and it doesn't break in situation 2. Try this practice problem. Suppose that a car is headed towards, or let's say we have 2 identical cars, and one car is headed towards a brick wall. And the second car is headed towards, wait for it, a haystack. This is hay. Yay! If you have a car headed towards a brick wall and a car headed towards a haystack, and suppose that both cars are approaching, I hate when it does this. Stop, don't do that, please. That's annoying. Okay, suppose that both cars, the brick wall car and the haystack car, suppose that both cars are approaching with an initial speed of 30 miles an hour. Which car will experience a bigger impulse, the car that hits the brick wall or the car that hits the haystack? Oh, wow, that looks like a backwards car. It's going towards the brick wall, it really is. Okay, let's give it wheels. Which car will experience a greater impulse, the car that hits the brick wall or the car that hits the haystack? Which one will experience the greater force and which one will experience the greater time? Go ahead and think about it for a second. Write down your answers in your notes. You should say that both cars will experience the same gympulse because both cars are going the same speed and then they both have the same mass if they are identical and they both will end stopped. So they both have the same change in momentum. They both have the same mass. They both have the same change in V. So they both have the same change in momentum. So the change in momentum is the same for both. But the car that hits the brick wall experiences that change in momentum in a very, very short amount of time. It is going and all of a sudden it is stopped. And so that brick wall is going to apply a big force in order to get it to change its speed in a very small amount of time. Meanwhile, the bottom car is going to come to a stop very gradually as it hits the haystack, and the haystack kind of moves with it. And so the haystack is going to apply a much smaller force as it slows it down in significantly more time. This is why you are told to roll with the punches, because if you roll with the punches, they hurt less. The next time that you get into a fist fight and someone goes for your face and they take a fist and they smash your cheek like this, when they do that, what you should not do is you should not steel yourself and hold your head and your face as straight as possible, an unmovable object, so that when the fist comes and hits your cheek, you stay still. That is not what you should do. No, when the fist comes and hits your cheek, you should roll with the punch. Move with it. Why? Because that fist has some momentum. And it's about to have a change in momentum because it's about to go from moving to not moving. And so if it's going from moving to not moving, then when it hits you in the cheek, you want that going from moving to not moving to last as long as possible. So you want it to go from moving, and gradually slow down to a stop. So you increase the amount of time it takes for the fist to come to a stop, and you decrease the amount of force that your face feels because of the fist. This is also, or let me back up here. I have one other application that I want you to kind of think through. Which one would experience more gym? Which one would experience more gym pulse? A bouncy ball that has not very bouncy at all. And it goes down and it hits the floor and it stops. Or a bouncy ball that goes down, hits the floor, and bounces right back up again so that it's flying back up through the air. Which one experiences more impulse, situation 1 or situation 2? The answer is situation 2 experiences more impulse. And here's why. For impulse, direction matters. Check out the change in velocity. In situation 1, the velocity is down and then it comes to a stop. So you have velocity that starts moving fast and then it ends. So that's a change in velocity. But in situation 2, you have velocity that's down, the bouncy ball comes to a stop, and then it bounces back up again and is going fast up. So in situation 1, you have velocity down, stop. V final is 0, V initial is V. In situation 2, you have V initial is V, V final is now negative V. So if you do V final minus V initial, then you have negative V minus V. And so then you have double the change in V. Delta, you have 2V is your change in V. Here your change in velocity is just V final minus V initial, but V final is 0, so you just have negative V is your change in velocity there. So notice my change in velocity is much bigger on a bounce, which means you get way more gym pulse on a bounce than you do on something that just goes and stops. This should make sense to you for a few reasons. First, because it is much harder to have something that is moving to stop it, then to turn it around and launch it back to the other direction. That is way harder than just having something that is moving that then stops. If you are trying to hit a baseball, it is way harder to get a baseball that hits your bat, bounces off, and goes back flying the other direction versus if you just have a baseball that hits your bat and stops and falls to the ground. It takes more force because you have to create a bigger impulse if you are going to accelerate something way more, if you're going to have it going one direction and then bouncing off the other direction. So a bounce always requires more impulse. This is why it takes way more force from your tennis racket to make a tennis ball hit your tennis racket and bounce back off again. It also takes more force if you're trying to bounce a volleyball back across the net. Bouncing something takes more force than something just coming to a stop. Here is another example. Recently, I have been learning how to catch things. When I was but a wee child, my parents said to me, Miss Wilson, you have no hand-eye coordination, so we shall not try to develop this skill for you. Which is actually very sad because I do think it's a skill that you could kind of develop. Like, I think it's something that you could get better at. But my parents did not think that that was something that I could get better at, and so I never learned how to catch anything. Well, the other day, this weekend actually, I was playing with a little bouncy ball, and what I was doing is I was tossing it back up into the air, and then I was trying to catch it on the back of my hand. Now, when I was trying to catch it on the back of my hand, what I kept doing, that was dangerous. What I kept doing, sorry, I'll make this bigger so that you can see too. This is just ridiculous. You're looking at a tiny little square. Okay, what I was doing is I was throwing it up, and then I would throw it up, it would come down, it would hit the back of my hand, and then it would bounce off. And I would say, this is no good. I can't catch it on the back of my hand. But then I learned that I knew something about impulse. And I said, no, I know how to catch a ball. I shall use impulse to help me. I said, if I want to catch it and I don't want it to bounce, what I'm going to do is I'm going to provide less force because I want to change its momentum less so that it doesn't bounce. And so what I did is I tossed it up, and then when I caught it on the back of my hand, and anyone who knows how to catch stuff knows this, when you catch something on the back of your hand, you want to start by moving your hand down so that I'm changing the momentum of the ball less. If I'm changing the momentum of the ball less because I'm moving with the ball, so I'm not saying to the ball, excuse me, sir, can you please come to a full and complete stop right now? If I give it more time, then that's less force. And so I can keep it so that instead of having a big force where it bounces back off, I make it nice and long. It takes very, very long to have that change in momentum. And so because I stretch out the time, then I have less force. And then my change in momentum is significantly less because I'm not making it bounce. I'm just making it stop. So there are some tips from a non-catching person to other people who already know how to catch things who didn't need me to teach them how to do that. And that's all for class for today, folks. Today we talked about momentum. Momentum is how hard it is to stop a moving object. Then we talked about our good friend Gympulse, which explains how it requires a force that is applied over a certain amount of time to create a change in momentum, which deep down is what impulse is. Just because something has a certain change in momentum does not mean that happens a certain way. So you can change your momentum by using more force, or you can change your momentum by taking that force and applying it over a longer amount of time. And that is all for today, folks. I hope you have a wonderful rest of your day, and I will see you all next time. Bye, good people.